Good morning, everyone. I'm Deepraj Pandey, and for my capstone this semester, I looked into trusted execution environments, specifically Intel's SGX. I'm just going to go give a very brief overview of SGX and then proceed to look at one of the use cases, key value stores, and then have a discussion around how we can take an existing application and port it to SGX. SGX is short for Software Guard Extension, and it's essentially a Intel's trusted execution environment. And that's just a fancy term for an isolated environment that's provided to user-side applications to run any of their secure computation. If we the reason we need this is because software these days deal with sensitive information like user passwords, health records, private encryption keys, etc. And if you look at the figure on the left here, the attack surface for a normal application is quite large. The OS already provides certain levels of isolation between processes, but even though there are attacks over there, but it's still there. However, an app has to uh, place a lot of trust in a larger area over here, the hypervisor, the operating system, etc. And if a malicious party gains access to administrative privileges, or your operating system itself is malicious, then an application's all of its secrets can be stolen. What SGX does in that case, or any trusted execution environment in that case, is provide an application a mechanism to create these secure, isolated memory environments, which allows it to run specific code that probably generates its secrets or deals with them. And it's only accessible to the hardware, and that results in a reduced trusted computing base because it's available in plain text to only these things that are in orange over here. And it's obviously it has extra on-die hardware, and that guarantees the isolation and through cryptographic mechanisms. The way it works is that a user application is allowed to designate portions of its code, which can be run inside these secure environments, and they're called enclaves over here in green. Um, and like a user process, an enclave has its own data and code sections, and everything that's inside it cannot be accessed by any of the other sections of your systems. Not even the parent process, which starts these enclaves. And every time data needs to be transferred between these two, there needs to be very strict marshalling, and these are set up through specific files that we're going to take a look later on. Um, and obviously, the code that you set up over here, say you have a key generation function and you want it to run inside a secure environment, you can set it up such that it's triggered from outside. And in that case, that function will be called an eCall, short for enclave call. And similarly, there can be functions on the untrusted side that can be invoked from inside an enclave, and those are called O calls or outside calls. Those are pretty important because you cannot do system calls from inside an enclave. That's one of the ways that the operating system is kept aloof from execution of this code over here. So what you'll essentially have to do is pass that data on to a proxy function that you would have set up over here, and the untrusted side is going to then invoke that system call. Like say you want to print something. Um, and the place in memory where all the enclave code is set up is this portion called processor reserved memory, diagram not for scale. Um, and the enclaves are broken down into these 4 KB pages, and these are called, and this portion is called enclave page cache, short for EPC. And the red portion the brown portion over here is your metadata that is required to handle the multiple enclaves that are running in a system. Now, one downside over here is that, like for every system, the PRM is limited to only 128 megabytes, and after the metadata, only around 96 megabytes is available for all the applications to use as their enclaves. But obviously, in Linux systems, there is demand paging available with extra encryption via the MEE. And the thing is, this portion of your memory is not accessible to anything else on your system. To your operating system, this PRM looks like a whole. This is essentially non-available memory. And on also all the EPCs, the pages over here are all encrypted by the MEE, and if there is anything that's trying to try a bus snoop attack or something like that, they're only going to see garbage value. There is encrypted data placed over here because It's outside there. The only place where the data that is being executed or being dealt with inside an enclave is available in plain text is on the chip itself, nowhere else. And obviously, SGX opens up a lot of opportunities for applications which can make use of these isolation. And one of the use cases that I want to talk about is key value stores. Think of these as just non-relational databases, but on directly on memory instead of your disk. These have been on the rise with the increased access to larger data centers, where you have literally access to quite literally terabytes of memory. And if an application prioritizes latency over anything else, or like say a reduced persistent support, in that case, these key value store applications for instance like Redis and Memcached will be used by the application. Um, and like in most production level applications, these are used these days. um, and because this is on the memory, and like given the low latency numbers over here, these applications are used to deal with say user session information, and that's when an application which is a running server, it stores users credentials, like it's the fact that the user has logged in, it's going to store that in a session store over here. And because it deals with sensitive user data, we need to make sure that like this needs to be secure, which is one of the arguments for taking up key value stores as SGX. Now there are obviously problems. Like, well, first thing is that EPC is limited to only 128 megabytes per system, and of which only 96 MB is available. And on top of that, there is a high latency, as every cache line is encrypted and decrypted during every write and read. Um, However, there has been prior work which has walked around these shortcomings, and one such project is Shield Store. It came out of a national university in South Korea, and it was published in Eurosys last year. Um, and the initial plan for this project was to set this up as a reproducibility study for Shield Store, and then experiment with updates to the existing design of Shield Store. But there have been problems. This is a complex piece of code, and despite being in contact with the original authors, there have been certain issues. And despite obviously setting up the prerequisites, there have been other issues with like memory reads, specifically when there is demand paging, when the size increases beyond 128 megabytes or 96 megabytes. So what we decided to do instead was to build our own key value store and start experimenting with it. Um, so and it's just a naive, and I'm calling it KVS right now. It's just a naive version. There are two code bases. One is the insecure version of it, and then the other one is ported to SGX. So I'm going to use this as an opportunity to discuss how you can take an insecure application and then start thinking of porting it to SGX. First step would be to just build your application, ensure that like it's not vulnerable to other common forms of attacks. SGX right now does not have support for, it will not protect you from cache timing attacks, and there are other SGX specific attacks as well, like foreshadow, etc. But that's beyond the scope right now. And then you rethink your design and then think of like what portions of your code need to be untrusted, like on the untrusted side, and what portions need to be on the trusted side. Keep the trusted side succinct, and then like just deal with data that you absolutely need to. And there are mechanisms, but like yes, you need to think of all of these. So what I'm going to do is like just discuss some of these functions, and then my version, my way of like sort of abstracting away the details to make these decisions. Please ignore these green and blue boxes and these arrows for now. So um, the first thing that I'm calling are these housekeeping functions. This is the backbone of your application. This sets up the control flow and then deals with the users. Here, user application would be a server which is trying to say store a session information here. So it's going to access one of these, call one of these functions, and here the server is using our KVS as a library, and then like it's going to give say like set in 127 you need to store some users information over there instead of this 7 over here. So this can be a typical command, and then like that, all of that needs to happen through these housekeeping functions. Right now I'm using these read instructions and clear instructions as simulation for typical user application. But yeah, then KVS operations are essentially your interface to your KVS, key value store. Init store, destro store will allocate, deallocate memory, and these are batch get and set operations. And internals are your atomic get, set, and hash functions, and usually you'll have this as a hash table. So the idea is that like your interface and like whatever deals with the whatever is the crux of your problem here, dealing with the user data, they need to be on the trusted side, and everything else needs to be on the untrusted side. And your housekeeping section of your application, those functions are going to initialize the enclave and then set up the execution flow and then like do what needs to be done after this trusted your enclave returns, and so on and so forth. Typical app structure would be like this for an insecure application. There will obviously be more files over here, but what I've done here is I've just taken all of those applications, functions that we discussed, and placed them all in this main.cpp. And when you finally port it to SGX, you will typically deal with two folders. This parameters header file has all the common hash defines between these two. For instance, the buffer size is set to 64, and that's defined here. But all your untrusted application code is going to be in the app.cpp file. This will be your housekeeping functions and everything else. And you will need to initialize your enclave and then check for errors over here. And every time you call an eCall, you need to check if it returned or if it actually executed properly. In your enclave folder, you have the enclave.cpp, which has all your trusted functions. Then in your config file, you are going to set up the your maximum heap size and then the maximum number of concurrent threads that will be running, that will be allowed inside this enclave. There is threading support, but it's kind of iffy, so I'm not discussing that right now. There is the header file, there is the linker script, and then that's your private key, which will be used to sign your enclave. And there is an attestation process as well, but I'm not going there right now. Then there is your very important file, your EDL. That EDL stands for Enclave Definition Language. This is where you're going to specify your function prototypes and then say which ones are going to be the interfaces into the trusted side and which are going to be the OCalls. It typically looks like a standard C header file. You have your trusted part, and then these function prototypes are essentially your interfaces into the trusted into your enclaves, and these can be invoked from outside your enclave but within your untrusted part. And these untrusted prototypes are basically this is the print function I was talking about. So these will be invoked. This can be invoked from inside your enclave. Then there are these keywords like in, string, and then user check. These are basically for your. There is a tool called Intel Edgearator R8R. And this is the marshalling that I was talking about. You'll be specifying exactly how long. If you're passing in an array, I don't have an example over here, but if you're passing in an array, you need to specify what's the size. So there will be another argument over here called size, and then you need to set it to something. You can always do something like there is the pointer and then be like an int size or something, and then here set up size is equal to size or something like that. So yeah, I'm not going to go deep into it. Let's move to the demo. Wrong side. I have SSH chain to the system, and I'm going to, let's check the basic version first. So here I have demarcated the portion which deals with the key value store between these equal to and this equal to. Anyway, so this is your housekeeping function, which is reading the workload file. The workload currently is basically a bunch of these set, say index and then 7, or say 1024 and then 7, or like basically it's just trying to set a bunch of these values, but I'm just setting it to 7 right now just to keep things easy and small. Then your init store is called, and then memory is allocated, and then secure set is called, and that whole workload is passed into it, and then it executes those instructions and reads them into the store. Then you use secure get, and then like I'm reading a bunch of these indices 1017, 1018, 1019. It's reading it successfully and printing it. Then so I'm calling this untrusted side, and I'm also saying value received from enclave over here because I want to keep the output similar so that we can see the differences when we run the secure version of this application. So what I'm doing in this function is this is another OCall. I'm simply passing where I saw this value, where I read this value. I'm just passing that address and also the value that I read there. And inside the application, what I'm doing is like I'm trying to dereference that address, and then I can successfully read 7. Then I'm reading the next index's value as well, and I can successfully read that as well. This was a bad idea doing just 7s, but yeah, it's happening. And then when when you read 1018, it's like it should be FE4 and it's the same address, and I can successfully do that, and so on and so forth. Then like eventually, like when you're done, like we deallocate the memory from the global store, and then we are done with it. Now let's move on to the SGX part. Make the application is built. Similar output here, the untrusted parts are basically your housekeeping functions. Enclave needs to be initialized, and then there are a bunch of these error checks that need to happen. And then like you're reading the file as usual, and then initializing. All of these are actually running inside the enclave. These are your untrusted code. So yeah, and then like you finally do, when you do a secure get after executing your set instructions, you can successfully read it. And then like similar function has been set up as an ocall over here, and I'm passing again the address from within the enclave. This is inside the enclave and the value. But when I try to dereference it outside the enclave, the CPU is jumping in right now and being like, hey, you are not inside the enclave and you cannot do this. Like the CPU is not in enclave mode, so these reads are not allowed. Similarly, for like if I want to increment the address and try to dereference them, I cannot read the values. But like same, like FFC was the last address, so 1018 should be at 004, which is correct. I still can't dereference, but like if the enclave is reading the value and then passing it back, it can happen. So yeah, and then finally like destroy store deallocates the memory, and then yeah, we're done with the application. Also, this was not like you cannot just typically send this out. Like we had to set this. I had to set it up as a user check in the EDL file. But like your usual data marshalling will require a size if you're going to pass in pointers, because this needs to go out as a pointer. But like if you do not want to give a size, then like here you have to put it up as a user check. But anyway, the next steps from here would be to obviously dive deeper into the SGX drivers, and like I need to troubleshoot like all these EWB calls. Every time there needs to be a demand paging for an enclave application, there are some issues on the system. And I've run into issues with both Shield Store as well as this application when we deal with bigger data sets. And then like obviously like meanwhile I'll keep working on like expanding this current design, and then accommodate like random character values, and then like also start building in cryptographic mechanisms into the KVS, and then start considering the threat model for this. And yeah, thank you so much for coming for the presentation, and the video ends now. I'll be around for if there are any questions for me. Thank you.